Welcome back. In this section, we're going to be looking at infinite limits. And by that, I don't mean limits as x goes to infinity. We've already seen that. Here, we're going to be looking at what happens if the function becomes infinitely large. So just to get ourselves started here, I'm looking at this function 1 over x plus 1 squared, which I know that that's just the 1 over x squared function shifted to the left, so it's got a vertical asymptote, x equals -1, and it's also got a horizontal asymptote, y equals 0, and it looks a little something like this. So for sure, if I were describing this function to somebody and I were talking about it with limits and I were saying, what's the limit as x goes to -1? Does that limit exist? For sure, the limit does not exist because remember, for a limit to exist, then that would mean f of x would have to be approaching some real number, and it would have to be approaching that same real number on the left and on the right as x approaches -1. But of course, for this one, f of x is not approaching a real number. It's becoming infinitely large. So what I might do instead is actually write this. I might write the limit as x goes to -1 of that function equals infinity. And so here I'm not saying that the limit now exists, but what I'm saying is this function is becoming infinitely large on both the left and the right side of 0. So basically what I'm doing is I'm describing how does the limit fail to exist. So when I say that the limit is infinity, that does still mean that the limit does not exist. The limit is not some finite number. However, it doesn't exist for that reason because the graph is becoming infinitely large on both the left and the right side of -1. So really, if you wanted to interpret it in words, you could say 1 over x plus 1 squared diverges to infinity as x approaches -1 on both sides. And that's basically what we mean when we say an infinite limit. So just as before, though, the both sides part is important. So if we were looking at 1 over x just itself, that one, I know it's got a vertical asymptote, x equals 0. And I know it looks a little something like this. Of course, it's got a horizontal asymptote, y equals 0 as well. And this function is not one that has a limit as x goes to 0. Of course, it's not a limit does not exist. It's not approaching a real number. But I also couldn't say limit x approaches 0 is infinity because it's not approaching positive infinity on both sides. I also couldn't say that the limit is negative infinity because it's not approaching negative infinity on both sides of 0. So what I should do really is describe what's happening near 0 with left and right hand limits. So same notation as before, I could say on the left side of 0, the function is diverging to negative infinity, so we're heading on downward. And on the right side of 0, we're diverging to positive infinity, so we're getting larger and heading upwards. So left and right hand limits are pretty common here when we're talking about these limits that are infinite limits, because for a lot of functions, if we have a vertical asymptote, if we have an infinite limit, it's a vertical asymptote, and they are not always ones where we're doing the same thing on both sides. A lot of times it'll be this case where on one side it's going downward and on the other side it's going upward. So now a formal definition for infinite limits, and this is similar to the delta epsilon limit definition that we gave before. So here we're coming up with a nice formal definition of what does it mean to say that the limit of some function is infinity. So for this, what we're saying, kind of like the delta epsilon proof, is no matter what big number you give me, so this is my as large as I want to get, there's going to be some closeness out there in the x direction. So delta is how close I am to c, to where my limit is looking at. So that if I am close enough to c, so x is close enough, the f of x being bigger than m, that's my y values are as big as my big value that I've chosen. I can get my y values to be as large as that or larger, however large I'd like it to be. So in other words, my y values are large. So if my x is close enough to c, then my y values become really large, and they can be as large as whatever large number you feel like picking. So if you had your limit as x goes to c being positive infinity, then if you wanted your function to have a y value that was bigger than a billion, you could find some closeness where if x was close enough, the y values would all be bigger than a billion. And if you wanted the y values to be bigger than a trillion, you could find a delta where if the x values are close enough, all the y values in that little interval are bigger than a trillion, and so on. The definition for negative infinity is similar. It's just now instead we've got some negative n. And so if we are close enough, then our function is more negative, larger in the negative direction, or further to the left on the number line. And of course, you could also make modifications of this to be left-handed limits or right-handed limits. You'd have to make the modification to what do you mean by close enough to c. So if it's left-handed limits, then its x is less than c. And if it's right-handed limits, x values that are bigger than c. But the idea is kind of the same. So that's our intuitive definition of intuitive meaning of it. So for this formal definition, intuitively what it means is for a limit to be positive infinity, if x is close enough to c wherever we're doing our limit at, the y values will be as big as we'd like, or in the negative infinity sense, the y values will be as small or far to the left on the negative side of things as we'd like. So I'm just going to do this just for once, just for fun, proving formally that the limit as x goes to 0 for 1 over x squared is infinity. And I'm only doing this once just so that we can see it in action. I'm not going to expect you to do this limited infinity proof. Or one like it. A delta epsilon one from the earlier sections, yes, that's fair game, but limit, that's an infinite limit, no, not so much. So same idea that I'm going to do as with the delta epsilon proof, though. I'm going to set things up first as far as the formal proof part, and then I'm going to do the rough work, and then I'll fill in the proof. So as far as the actual formal proof goes, just like the delta epsilon proof where we started off saying, well, let epsilon be some bigger number than 0 or number larger than 0. Similarly here, our proof is going to start off with us letting our number m be bigger than 0. And then what we have to get is we have to start off with if we're close enough to c. So in other words, if 0 is less than absolute of x minus 0, less than delta, then, and bunch of stuff to fill in, and we'll hopefully get to therefore 1 over x squared is bigger than m. That's kind of what we have to get to. That if x is close enough, close enough to where we're taking our limit at, which is at 0, that our y value will be as big as our pre-chosen big value. So now what we need to do is fill everything in the in-between. You'll also notice I've left a little gap here, and the gap is going to be for me discussing how I choose delta. So remember, just like before where delta would depend possibly on epsilon, here delta might depend on what my choice of m was. So now let's go back and let's figure out the rough work side of things. And so what I need is I need 1 over x squared to be bigger than m. And of course, m is a positive number and x squared is a positive number. So if I move the x squared up, that doesn't change my inequality. And if I move the 1 down, that doesn't change my inequality. And one thing that I could also do is maybe just rephrase it like this. So instead of it having 1 over m being bigger than x squared, I could say x squared is less than 1 over m. Now, again, I'm going to point out the obvious. X squared is going to be something positive, and we said before that m was positive, so 1 over m is still positive. So for sure, I can take square roots of these numbers. One thing that is true for an inequality is if you do have an inequality a less than b and both numbers are positive, or rather non-negative, then you can take square root and have the inequality still being preserved the same direction. So this is a fun fact about inequalities. So if a is less than b, then square root of a is less than square root of b. So I could say then if x is squared is less than 1 over m, then I can conclude that 1 over x would need to be less than square root of 1 over m. And no, it's 1 over x. Square root of x squared is x. Oh my goodness. There we go. And so now I'm getting to where I need to be here, because remember at the very beginning of our proof, we're going to start off with absolute value of x minus 0 less than delta. And so I'm going to sort of do a little bit of a workaround here, and I think my plan is the following. It looks like if I have x less than square root of m, then that means x minus 0 would be less than square root of 1 over square root of m, which makes me feel like this is my choice for delta. My delta should be 1 over root of m. So let's start off with that. I'll make my proof. I'm starting now letting m being bigger than 0, and now I'm going to make my choice delta to be 1 over m square rooted. Okay, so what I've got now, I can say, well, we're starting off with x is close enough to 0, so x, the difference between x and 0 absoluted is between 0 and delta. And then I can, of course, say that if x minus 0 absoluted is less than delta, then that's just absolute of x. And delta is the same thing as 1 over m square rooted. And now the next part, I can say to myself, well, for sure, if I had this, I could, with an inequality, since x is absoluted, it's going to be a positive number. 1 over m is going to be a positive number. I also know then that if I were to square the left side, that it would be less than squaring the right side. And now here's where I'm going to make a little bit of an argument to myself. So I'm reminding myself here that, of course, I took x, I took the absolute value, and then I squared it, but the squaring does the making things positive already, so the absolute value really isn't needed anymore. So I could really just say now on the left side, it's just x squared. And I've got 1 over m. So now we're almost finished. I guess I need to make just a little bit more room for myself before I can make my conclusion. I guess I was a little optimistic there. I'm just going to need to rephrase this. And so here what I'm going to rephrase this as is m is less than 1 over x squared, or in other words, 1 over x squared is bigger than m. So our function is larger than m. And now we've shown it. We can say now, therefore, the limit as x goes to 0 for our function is positive infinity. So pick any large number you want. Here's how close you need to be so that if your x values are close enough to 0, that closeness, then your y value will be bigger than your pre-chosen really large y value. So in other words, as we get closer to 0, the y values get as large as we'd like them to be.